Here we go, rabbits. At the start, they can breed freely, and that's the exponential growth. I'm not going to put the constant there yet, but it's the basic reproductive constant R. However, as the population grows, especially here in Europe, where we don't have too much room, there is less room for the rabbits. There is less food for the rabbits. So what's happening is that the reproductive constant actually decreases. That's how we can see mathematically what's happening. They are breeding less fast. Now, again, there's a good question how to describe it mathematically, and there are several interesting candidates, and one of them works like that. The new breeding constant is based on R, which is the basic breeding constant for rabbits that are free to multiply and with lots of food. I divide it by K. What is K? Well, K is something which is called carrying capacity of the environment. Intuitively, I see it as the exact number of rabbits that can live there comfortably, or the amount of food divided by the needs of one rabbit, or something like that. This is simply how many rabbits the environment will be able to support. And, very important factor, K minus Y. So this is the new breeding constant. And it also depends on Y. Let's have a look at it. What's happening here? R over K times K minus Y. Well, there are two interesting situations. The first interesting situation is when the population is very, very small, which essentially means that it's much smaller than the capacity. So let's say that you have Australia, which can support millions of rabbits, but you have just 100 of them. In that case, in this part, Y is negligible compared to K. We can ignore it. And this breeding constant is something like R over K times K, which is R. So at the start, those rabbits or whatever are breeding exponentially. This is just like the exponential growth. This is R. The other interesting situation is when the population is very close to the carrying capacity, or the capacity of the environment. In that case, you get something like R over K times 0. And the breeding constant is 0 and the population stagnates. So these are two very interesting situations. So the population first shoots up very fast, then something happens, because this is getting smaller as the population grows. You can see it here. The bigger Y, the smaller this factor. So the growth slows down, and as the population reaches, if it reaches, we will see it soon, if it reaches the capacity K, it slows down to crawl, this growth. So that's the behavior that I expect. Let's talk a little bit about slope field. That's a good question, essentially. I look at this equation. By the way, there are no restrictions. Nothing wrong with Y, and nothing wrong with, let's say, T for time. So I can handle it as an autonomous equation without any restriction at all. So we have a two-dimensional plane, but actually I restrict myself intentionally to Y non-negative, because we're talking about populations here. Okay, here we go. I'm just looking up here. I can see one stationary solution, which is 0. So we have it already here. And then there's a second stationary solution, which is K. And now what are the signs? Well, up here, when Y is infinity, then this is infinity times negative infinity, negative sign here, and these are positive constants. Okay, let me also remark that R is positive. Okay, so these are positive constants, also K, but that's automatic. Okay, let me write it down. K is also positive. So positive, positive, negative, positive, decreasing. What happens if I'm between 0 and K? If I'm between 0 and K with Y, then this is positive, 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 everything is positive. Which sounds positive. Wonderful. That's the slope field for my equation, which, by the way, is called logistic growth. And I look at it, and I can see that this stationary solution is stable. which is very nice in biology. However, this one is unstable. Which means that once you have some population, it will never die out, but it will tend towards this equilibrium, which is actually the capacity of the environment. If you put more population into the environment, let's say that you import rabbits from elsewhere, and you overfill the environment, then the population goes down because there is not enough resources, makes sense. And again, it approaches, it seems from the picture, this carrying capacity K. So from the ecological point of view, that's a nice behavior, because the population, no matter what it is, tends to go towards some equilibrium with the environment. Okay, so far our analysis gives us interesting answers. So let's try to solve this equation. That's a very good question. How much room will I need? Okay, here. Is this a separable equation? The answer is yes. I can move y's to the left without any trouble. Let's write it down. dy over dt is r over k, k minus y times y. Okay, stationary solutions. Y is equal to 0, y is equal to k. Otherwise we divide, and we get dy over k minus y times y. So far so good. And I'm also going to move k to the left. And this is r dt. And now we don't integrate. Why? Because, well, we will need to handle this integral. And this area will come handy because partial fractions. Here we go. K over k minus y times y is supposed to be something divided by k minus y plus something divided by y. How did it go in calculus 1? Okay, covering method. I cover y and I put 0 for y, put it here and I get 1. That looks nice. I covered this and the root here is k. So I substitute k over here for y and I get 1. Really? Isn't that nice? So let me see. If I multiply it, y, k minus y cancels, I get k. Yeah, that's correct. That's very nice. Okay, now we can integrate. So I just imagine that this is here, and I integrate. Okay, how do I integrate? This is logarithm, definitely. And this is also logarithm, but there is the minus in front of y, which comes out after I do the substitution. So it looks like that. And on the right, there is RT plus C. Okay. Can we get rid of logarithm? Not yet, because there is 2 of them. And how do we get rid of logarithm? We apply exponential, but to the equation. That's important. I cannot apply exponential here. I have to apply it to the whole left-hand side and to the whole right-hand side. Okay? That's important. And if I apply exponential to the left-hand side, I will have to work it out a little bit more. There will be some 1 or 2 more steps. So I will save some time and do those steps now, just to recall some nice formulas. Logarithm of y over k minus y is equal to RT plus C. And now when I applied exponential to the whole left-hand side, it cancels immediately with logarithm. Yeah, that's nice. And then I get rid of the absolute value, and I get y divided by k minus y is equal to plus minus e to c times e to RT. Okay, now I need to figure out what is y. Yeah. Okay, y. Y is my target. Y is equal to k minus y times d times e to RT. Okay, what's happening now? I'm going to multiply out the bracket. There will be part without y. This one will stay on the right. And it looks like this. kd e to RT. Now the y part will be moving to the left. I factor out y, and it stays here. and the factor will be divided. So what's the factor? I multiply, I factor out 1 plus d e to RT, t greater than or equal to 0. So that's a formula. And as usual, this expression here can never be 0. So d can never be 0 here in this picture. But if I allow it to be 0, I will get what? I will get 0. And I'm recovering my stationary solution. So that's the usual behavior. However, there is also a second stationary solution. Where is it hidden here? And the answer is it's not there at all. I cannot recover this stationary solution, y is equal to k, from this formula. So that's a new behavior, but we actually, well, I talked about it earlier. When we covered separation, I said, do not rely on your stationary solutions to be always included in the formula. This need not be true. The fact that this 0 were included, you should see it as a bonus. Okay? So if you want to talk about a general solution, we should add this. Or yt is equal to k, t greater than or equal to 0. And now, this is a complete description of the solution. Okay, let me put t here. And you could call this a general solution if you want. What can I expect from this? Well, we can all visualize the stationary solution k. It's a constant function, but how about this one? E to RT. R is positive. Yeah, it's written there. R is positive, so that's an exponential, it goes up. I multiply by constant, which, well, it could be negative, and then I mix it up. Can I visualize it? The answer is, I guess I'm not experienced enough. Now, we will soon ask Maple about a picture, so that we can have some idea how these solutions look like. Of course, we do have some idea from the slope field that we sketched before. So, just out of curiosity, let's confirm something. I look at this formula and I say, okay, what happens if we send time to infinity? Well, for this version, it's obvious. The limit is k. How about this version? Well, when time goes to infinity, r is positive. Positive number times infinity is infinity. E to infinity is infinity. So I can see two infinities here, and they dominate. Compared to one, they win. Okay? Well, unless d is 0, that's a special case. When y is 0, the limit is 0. So let's talk about positive d's or negative d's, non-zero d's. And then this dominates, and I could use some cancelling, for instance, to see the outcome. That would be a good idea. So I'm going to cancel or divide both numerator and the denominator by the term which I feel is dominant. That's what I learned in calculus. The dominant term exponential, I divide, and it becomes this. Kd on the top, e to negative rt plus d in the denominator. How much is it? Well, negative r is a negative constant times infinity is negative infinity. This goes to 0, this exponential thing. And because it goes to 0, the outcome is kd divided by d, which is k. And as I said, this is true whenever d is different from 0. That's important to notice. So, here is the conclusion. We have one exceptional solution, which is the 0 solution. This is the unstable equilibrium. But as soon as some solution is away from 0, which means d is non-negative, then all the solutions at infinity tend to k. So this picture sort of seems to be confirmed. Okay? Let's see what Maple thinks about it. I have a picture here ready for you. This is the actual slope field, not just a sketch, but the actual slope field. We can see the directions, the arrows, they flow nicely. And there are some blue curves. And let's say the second one from the bottom. You can see the exponential growth at first. That's the exponential. And then it levels off towards this equilibrium k. If the initial population is too large, which is the top curve, it decreases, and again it goes to this carrying capacity of the environment. So this all works out very nicely. So that's the logistic growth. Now you may feel that we had enough population ecology or population dynamics, so let's talk about something else. The logistic growth is actually used in medical field because it describes rather well the growth of tumors or cancer. which is fairly important because when they try to cure cancer, they are essentially killing it by giving the patient poison. And the trick is you want to kill the cancer without killing the patient. That would be nice. So the more they know about the growth of the tumor, the better they can judge the doses for the poison. And quite recently, accidentally, I stumbled upon an interesting article by some physicists, by some medical people from research, and they were comparing 7 different mathematical models of tumor growth. One of them was actually the logistic growth. So this is really used by medical profession, and they actually compared the data which they had on the tumor growth, on the actual situation, and they compared it with what the mathematical models, the 7 models, were actually predicting or showing. And they had some interesting conclusions. So for instance, depending on the kind of the tumor, of the type, different mathematical models turn out to be slightly better, which is interesting. But what was perhaps the most interesting part for me, that in some situations, for some tumors, actually it's not quite clear which model is the best one. So there are several candidates, and based on real-life data, you cannot really distinguish which one of them is the right one. And that's a problem, because you have some data, and I have 2 competing models, and they sort of look both similar to the data here. And you want to make a prediction, and those 2 models, they do that. And that's very unpleasant. Modeling real-life phenomena can be very, very difficult, and therefore predictions can be difficult. You probably notice that there are lots of predictions about economy, about things like that, and very often they are wrong. Well, that's because it's not quite obvious which model is correct. Economy is a prime example because economy deals with people, and people are really difficult to model mathematically. Why? Because they don't follow rules. They do whatever they feel like, and people are bad for mathematics. I mean, as objects, mathematicians are fine. So that's an interesting thing. So logistic growth, medicine, tumors, things like that, very useful. And talking about economics, actually people in economic field, they actually use logistic growth to simulate, how would I say it, the spread of innovation in society, which is interesting. I didn't know about it. Again, accidentally I found out. So the logistic growth, although it looks also very simple, it can be quite useful, and actually it's quite faithful. Human population actually follows logistic growth quite well. That's a good balance, because if you want to make a model more precise, it becomes more complicated, and then you cannot solve it, and you cannot analyze it perhaps that well. So that's a fine balance. People tried different ideas how to change this breeding constant based on the population. So there are some competitors, and they have some advantages, disadvantages, but the better you want to have it, the lower the chance that you will be able to handle it, actually. So yeah, that's pretty sad. Okay, that's the logistic growth. Let's play a little bit. We now know that the logistic growth is a much better model for population because it takes into account limited resources. What if somebody comes in and start messing up with the population by taking away a constant chunk of it? So this will be the logistic growth with harvesting. Y prime is equal to R over K, K minus Y, times Y, minus the harvesting, constant harvesting. That's a model which is of special interest to marine biologists. They also use differential equations. We have some fish population, let's say cod, or tuna, or whatever. And if there were no humans, they would breed according to this. Well, perhaps quite not, because they're predators. If you want to put predators in the picture, we need another variable for the predator population. We are not ready for systems with more unknown functions. But we will in a few lectures, well, in a few months, okay? And then we will return to this. Very nice. But just one population. If you leave it alone, it's essentially a logistic growth. But here come the people. And the question is, what will it do with the population? We definitely do not want to destroy the cod population, because then there will be no more cod to eat. Yeah. Here we go. How does it behave? That's a good question. I could try to solve it by integrating, but you can notice that using partial fractions here would be really, really hard. I mean, not hard, but messy. It gets ugly. because we would have to somehow handle the quadratic polynomial. Not very nice. Let's have a look at it. What kind of quadratic polynomial is it? I guess I can factor r over k. And what we are left with is minus y squared plus capital Ky. So far so good. And I've been factoring r over k, so there must be minus hk over r. So if I want to integrate, I would have to take this quadratic polynomial and somehow handle it, which is not very easy. The formulas would be real ugly. So instead, let me try just a sketch of the slope field. Okay, I'm inquiring about the sign of this thing. R is positive, K is positive. So I just inquire about this quadratic polynomial. Okay, how about the roots? That's a good question. Okay, let's put it here. How about the roots? Y is equal to, why not, let's say, because these will be the stationary points. Stationary solutions or equilibria. Quadratic formula, most likely. Okay, here we go. Minus k plus or minus square root k square minus 4 minus 1 makes it into plus, minus makes it into, okay, minus 4 hk over r. Did I make a mistake somewhere, anywhere? Nope, I don't think so. Divided by 2a, which is minus 2. Can I make it somehow nicer? That's a good question. I look at it and I don't feel that it can be improved much. Okay, here we go. Minus minus. So it's k over 2. That's the basic level for my two stationary solutions, or for my two equilibria, if there are any. Then there will be minus plus square root. And now I'm dividing by 2. I put it under the square root and becomes 4. And it's k squared over 4 minus hk over r. Okay. Equilibria. Do they really exist? That's a good question. It all depends on this discriminant, they call it. I learned this in elementary school, so I forgot. I just know how to use it. I don't know the names. So this thingy over here should be preferably positive. If it's positive, then I get two stationary solutions, two equilibria, and I know how to handle this. This will split into factors. Okay, what's the condition? Okay, the condition will be here. K squared over 4 minus hk over r should be positive. So I'm going to multiply everything by 4, I'm going to multiply everything by r, and divide by k. And when I do it, I get k r should be larger than, and I was multiplying by 4 and multiplying by r and dividing by, so it's 4h. That's it. So my condition is that h should be less than 1 over 4 kr. That's the condition which bounds the harvesting from the top. It says the harvesting shouldn't be too much. Okay, here we go. First situation, h is less than 1/4 kr. How will it look like? Well, here we go. Two stationary solutions. Notice that k over 2, if you square it, you get k squared over 4, and then there is the square root. So without this term, these two would be the same. But I'm actually making it smaller. So I have k over 2, and then I'm subtracting and adding something which is smaller than k over 2. So k over 2 is somewhere here, and I move it down and up by some amount, which is not reaching all the way down below the x-axis. It stays here, and it stays here. That's the two stationary solutions. Let's say with a tilde and with a hat. Okay? This one has a plus, and this one has a minus. Two stationary solutions. And now I'm going to imagine that I factored this out into two factors. That's what happens here. It becomes like that. And there is a minus in front of y squared, so this is a parabola which goes like that. So when you think about it, it doesn't take too much effort to see that when y is infinity, this will be negative infinity, and I get a decreasing picture. Here, increasing. Here, decreasing. So this is actually a stable equilibrium, and this is unstable. So what does it tell us? This tells us a story which actually is quite reasonable when you think about it. If the harvesting is not overdone, if I harvest reasonably, if I am not too greedy, then the fish population will be stable within some limit. I shouldn't, well, if the population is too small, then it will simply die out with harvesting. Okay, but if I can keep the fish population at a certain level, then it will be stable. It will tend to go towards this upper equilibrium, which is a good situation. Okay? How much harvesting can I do? Well, it depends on the carrying capacity of the environment and on the breeding constant of the fish. The more the fish multiply, the more can I actually take away from the population. So this all seems to fit. Okay? What happens if I start increasing the harvesting? What happens when h gets larger and larger and larger and larger? Well, I will be making this number larger, so this whole number, because I'm subtracting, will be smaller. It will be getting closer to 0. These two equilibria will be getting closer and closer to k over 2. So the safety strip, this is a safety strip. If I keep population here, it's safe. The safety strip will be getting more and more narrow. There will be a very narrow band here of increase and decrease up here, but this one is okay. It simply still means that the population goes towards this equilibrium. But this strip will be getting wider and wider. I would have to be more and more careful about not actually killing out those fish. So by increasing the harvesting, the situation is becoming more volatile. I have to be more careful, more dangerous. Of course, what happens when h is equal to 1/4 kr? That's the key question, because that's where things get really interesting. And the answer is, well, there will be just one equilibrium, namely k over 2, because then this square root will be 0. Just one equilibrium. Now, what happens with the sign? When I have a multiple root, it means I can complete a square. I factor out minus and I complete a square, so it will be minus something squared. That's how it looks like. Minus something squared. The sign is negative and negative. This is a very dangerous situation. If the population is large enough, it will go towards k over 2, but if by some accident, and something may happen, a volcano blows up or something, the population drops below k over 2, it dies out. And it will be close to k over 2 because it will be approaching k over 2. So this is a very, very tricky situation. You start with some population and you start harvesting at some rate, and the population goes here, whether you like it or not. And then this is a very sensitive, very vulnerable. Whatever small problem happens, the population goes down. This is very bad. So you definitely do not want to see that. Well, what's the last possibility? When you harvest too much. When you harvest too much, then there are no real roots. So this will be a quadratic factor which does not have a root, and there is minus in front of y squared, so the graph looks like this. This is always negative. And the picture looks like that. So no matter what you do, the population dies out, which is common sense. If you harvest too much, you simply eat it all. Okay? So that's an interesting use of logistic growth with harvesting. You can play with it like that. You can make little analysis. What people do in marine biology, they're actually trying to determine reasonable amounts of harvesting which they can allow people to do. And then you have some limits for the fishermen and things like that. This is actually all based on mathematical modeling, I learned. Okay. So much for the logistic growth. With harvesting, let me just show you a few pictures. What I did over here is I took a certain K and a certain initial value, Y naught. I start from a certain population of fish. So you can see the environmental limit, that's the red curve. I start at with some population, and then I tried different harvesting levels. And you can see that for small harvesting, the population went up, sometimes quickly, sometimes slowly to this level, this carrying capacity. But if I overcooked it with harvesting, the population dies out. Okay? So that's the outcome of compute trying to solve this differential equation. And that's it for the logistic growth. Let's see what's next.